today. So as you know, today we have the part 2 training for the cable stayed bridge design. And last time what we did is we checked the general concept, the modeling procedure and design procedure of cable stayed bridge. And also we checked the nonlinear effect and when we did such nonlinear analysis in the cable stayed bridge. And also we mainly checked the initial cable force, what was the traditional method and which method is provided in MIDAS 7 with the details usage of the unknown load factor function and the constraint condition and the influence matrix. So you must remember those topics. And today main topic is about the construction stage analysis. So last time our main topic was about initial state, which is considering the final complete state of the cable construction. But in the real construction, we need the jacking force for each of the construction stage. So how we can determine it? We want to check that part first today. And also after the construction stage analysis, for considering the moving load effect or the dynamic analysis like the eigenvalue or time history, in that case we need the additional analysis in the post-CS. So how we can perform and which element is supported in MIDAS. So we want to check a little more about this and some result functions, especially for the cable elements. So let's check the details. So it was the procedure we discussed last time, and we checked more details about the determining preliminary cable force, which is also called the cable force in the initial state. And we wanted to check now the jacking force in each construction sequence. So what is the method for finding this jacking force for the cable pretension force in each of the construction sequence? So to design this cable stayed bridge, its construction sequence should be defined to check the stability during construction. Structural system could change significantly based on the erection method. And the change of the system during the construction can result in more critical condition for the structure compared to the complete final stage. So accurate construction stage analysis should be performed for designing this type of the cable stayed bridge to check the stability and to review the stress of the structure. So construction of this cable stayed bridge can be classified into forward analysis and backward analysis based on the analysis sequence. Forward analysis reflects the real construction sequence, whereas backward analysis, just like this figure, is performed from the state of the finally complete structure for which initial equilibrium state is determined, just like the last time we checked. And then each of the elements and loads are eliminated in the reverse sequence to the real construction sequence. So this will be the first stage in the backward analysis, and we will try to eliminate each of the elements and the loads. So final construction stage will be just like this, without any cables. Comparing to forward analysis, we can easily find the cable jacking force in this backward analysis. However, the backward analysis cannot consider creep and shrinkage effect, which means we cannot consider this analysis type in the concrete stack cable-stayed bridge. For the concrete girder, so we need to go for the forward construction stage analysis, which requires many try and error. And also there is one more limitation in the backward analysis. So in the backward analysis, at the key segment closure, the shear force and the bending moment should be close to zero. However, if the bridge geometry is non-symmetrical, not like this type, but if the geometry is like the non-symmetrical, in that case we cannot get the zero shear force and the bending moment. So we cannot apply this backward analysis in case of the non-symmetrical cable-stayed bridge. So there are two limitations in the backward analysis. One is we cannot consider the creep and shrinkage effect. The other one is we cannot apply this to the non-symmetrical cable-stayed bridge. But even though it has many limitations, finding the jacking force is quite easy in this method. So as a first try, maybe this method can be used, or for the steel girder cable-stayed bridge, this method must be very useful. And let me show you with the model for this. So this is the final construction stage, and if we check from the first stage, this is the first construction stage, which has all the elements and the forces. And as the stage goes on, we eliminate the key segment first, and then first cable will be eliminated, second one, the outside one I meant, and then third one, so on. So just like this sequence, we eliminate each of the cable and the girders up to the final stage. In this case, what is the jacking force? Sometimes the users are confused. They think this value that we enter in the pretension, this must be the jacking force, but it is not true. This value is just the value which was required for this finite element analysis. It's nothing about the real construction value. Then what is the jacking force? We can check jacking force from the member force of the cable. So in this bridge, I will go to the truss force. And then in the first stage, which is the complete state. And if you see here, the first cable will be eliminated in the CS2. Let me change the stage to CS2 like this. Key segment is eliminated in the CS2, and in the CS3 you can see this cable is eliminated. It means right before this cable is eliminated, so in the CS2 we can see their cable force. This value is the jacking force we should apply for this cable when we install in the field. What about this cable element? So it's same. This cable will be eliminated in the CS6, as you can see. In that case, in the CS5, we can get their cable jacking force in CS5. So this value will be the jacking force. So right before the element is eliminated, that value is the cable jacking force in the backward analysis. So if we find the initial cable force in the complete state that we checked last time, if we have that cable force and then using the backward analysis, we can easily check the jacking force by just making the construction sequence in the reverse order. Then we can easily get this jacking force. And let's move to the forward analysis. So forward analysis reflects real construction sequence, just like this figure. And it takes more time for the designer as they should conduct the try and error analysis to determine this, the limiting member force due to the cable tension up to certain range. They know the initial cable force. So next step is finding the jacking force. And this jacking force, finding jacking force requires many try and error procedure. So this flow chart shows the process. Firstly, we perform the final stage analysis. And with certain constraint condition, we find the final stage cable force. Then we perform the construction stage analysis. So with this construction stage analysis, we verify the member force or the deflection of the girder, and if they are not satisfied, we should go into the previous stage again and again. So with this try and error procedure, we could finally find the cable force in the construction sequence. So in the forward analysis, again, what is the jacking force? Jacking force is same, so we can check the jacking force using the truss force function in MIDAS Civil. So in case of the forward analysis, right after that cable is installed, at that time we can check the cable force, truss force. This value represents the jacking force which should be applied in the installation stage in the real construction. So we should not be confused with the pretension force entered in the model file and the jacking force. They are not the same value. So backward analysis or forward analysis will be taken by the engineer depending on the type of the structure. And for this forward analysis, we could check. Backward analysis had many limitations. So for the concrete girder or non-symmetrical cable stayed bridge, we should go for the forward analysis. And how we can find the cable jacking force more easily in civil? There are two methods in civil. One is, you may know, Lego fit force. So with this Lego fit force functionality, the additional pretension loads which are introduced during the installation of the cable are calculated and member force are preloaded at the key segment such that the member force at the key segment closure are same as those the complete state. So Lego fit force can be classified into two different force. One is Lego fit force for the truss element, for cable, and the other one is Lego fit force for the key segment. Firstly, if we think about the cables, there will be the displacement at each end of the cable at the stage immediately before the cables are installed. And using the displacement at each cable, like this displacement will occur, and then the program calculates the additional cable pretension, which is the delta T in here. The difference between the cable length at the complete state and the cable length during the construction. Comparing this, we can get this delta T, the additional cable pretension force. And this additional cable pretension is added to the initial pretension, which has been determined in the initial state analysis. So by the summation of the initial state cable pretension force and the additional pretension force, finally the cable pretension will be determined in the forward analysis. So using the additional deformation occurred in the cable, the program calculates the additional cable pretension force, and this will be applied in the program. So that is the Lego fit force in the cable element. What about the Lego fit force in the beam, the key segment? Let's assume that we have the cable state bridge of the 3-span continuous bridge. If the key segment is closed in this state, no member force takes place at the key segment, and there is the discontinuity between the cantilever and the key segment, just like this figure. You can see their deformed shape is like the discontinued. So to connect the key segment to each cantilever member continuously, just like this bold line in black, Lego fit force function calculates the specified displacement required at each end of the key segment and converts that specified displacement into the member force applied to the key segment. So this key segment, which has the shape just like this, but in order to make this continued shape, the additional force will be applied to this key segment. So it will be deformed just like this shape. So, So they will have the continuous condition from the last cantilever part into the key segment installation. So additional force will be applied to this key segment. That is the Lego fit force in the beam element. So we have two different types of the Lego fit force, and they will be automatically calculated and applied in the program by checking on this option. So for applying this Lego fit force, we have to calculate the tangential displacement first by checking on this option. And this Lego fit force will be checked on. And we should create the structural group for the truss and the beam element for which the Lego fit force will be calculated. So definition is very simple. Then what will be happening? After the construction stage analysis, program will apply the pretension force as a summation value of the initial cable pretension force and Lego fit force. The summation value will be applied in the analysis, and then this forward analysis will be performed. So let's check with the program for that. So in this analysis, we have determined the cable pretension force from the initial state analysis. And then we want program to calculate the Lego fit force. So make the structural group. In this structural group, we want to calculate the Lego fit force of this cable and the key segment. This element is not actually required. So we need to define each of the cable and the key segment. So go to the construction stage analysis control dialog box and then check on this option and select the desired structural group. After that, once we perform the analysis, if we go to the results table, we can get the Lego fit force table just like this. So this was the initial cable pretension determined from the initial state. And this value is the Lego fit force calculated by the program using the deformation of the cables. And this summation, which is the sum column, these values were applied in the analysis. So this value is the one applied pretension load, and this is not the cable jacking force. Again, what is that cable jacking force then? In the stage 4, this first cable is activated, and jacking force is this value that we can check from the truss force. Also for the next cable activated in the stage 6, so this cable jacking force can be checked from this value. Same for the other cable. Once they are activated, we can check their jacking force in each of the construction stage. So that is the Lego fit force and how we can check the jacking force in the forward analysis. This Lego fit force function is very useful and easy to use, but there is one limitation in MIDAS Civil. We cannot consider creep and shrinkage option. So if we want to use this Lego fit force function, we can try to find this cable pretension force considering the Lego fit force first without creep and shrinkage. After that, we can update this value into the model and we can consider the creep and shrinkage and manually adjust cable force a little bit more. So that was the one limitation MIDAS Civil had. We cannot consider the creep and shrinkage in the Lego fit force function, but not the creep and shrinkage, we can consider the large deformation effects in the Lego fit force. You know, if in case of the long span cable stayed bridge, as mentioned last time, we need to consider the nonlinear effects, just like the stone cutter or stone bridge, which has the span length, like the more than 600 meter. So in that case, we can consider this nonlinear effect, and Lego fit force and large displacement analysis can be performed at the same time simultaneously. But creep and shrinkage and Lego fit force, it cannot give you the right value. Actually, analysis will be performed, but you cannot get the reasonable results with the creep and shrinkage and the Lego fit force. Let me go back to the program. So that was one limitation of MIDAS Civil Lego fit force. Now we have another function in Civil, finding the cable jacking force in the construction stage using unknown load factor. I think you must be familiar with the unknown load factor function now because we have discussed last time about this. Last time what we did is in the final state, without the construction stage, we have tried to add the constraint condition, and we checked what is the object function, how the optimized solution has been found depending on each of the function, and we can limit the value of the unknown factor as the negative or both positive value. And this same function can be used in the construction stage analysis. How to use that? Let me explain you how to use that in the construction stage. So in this test model, this is the order of the construction sequence, stage 1, 2, 3, 4, 5, 6, 7, 8, so on. And as you can see, there are the stages that cable is newly activated, like stage 2, 3, 6, 7, 10, and there is the additional jacking force required to install the key segment. So unknown load factor, we need the unknown factor for the stage 2, 3, 6, 7, and 10, 14. So in the program, let me show you how we could define it. Firstly, we need to specify the construction sequence in the first stage, second, third, fifth, seven, sixth, seven. So construction has been going like this. And if you see the cable pretension at the moment, they are just entered as one unit value. With this state, we just perform the construction stage analysis. And then we can go to the unknown load factor. And this stage that the cable is newly activated, we can check on this option so that program can find the cable pretension force. Similarly for the other stage that mentioned in the previous slide. So after selecting the desired stage, and we can add the constraint condition. For example, we can restrain the member force, or we can restrain the deflection of the pylon. Make the constraint condition is just same, and this object function or the unknown factor sign option is also same. Then we can calculate the unknown load factor for construction stage. So firstly, program tries to find the construction unknown load factor function, as you can see. And this unknown load factor can consider the nonlinear effect and the creep and shrinkage in order to find this pretension force with considering the changes of the element. The program requires the iterative analysis. So that iterative analysis can be specified here. For example, number of iteration will be 5 with a certain tolerance, and then program will try to perform the analysis again. And with each of the iteration, they will try to find the new cable pretension force. So once the analysis is performed, for example, in my computer, the additional model with the different number has been created. If I open the model file, which has the number 2, in the case, the program will automatically update the cable pretension force. As you can see here. So this force is automatically updated with the iteration process. So this is the way how we can consider the unknown load factor function in the construction stage. So in the unknown load factor, specify the final construction stage in here and make the similar constraint condition, and then select the stages that cables or the key segments are newly installed. And why the iteration is required? So this is required when the element force is being updated due to the creep and shrinkage effects or due to the nonlinear analysis effect. So when the stiffness is being changed, program cannot find the pretension force at once. Because of that reason, so we need the iteration analysis, and program will make the additional model until the unknown. They will make the additional model which has the new pretension force, and they will make the iteration analysis again until the unknown load factor becomes becomes 1. So in this model, for example, so if we see the unknown load factor, so it's almost like the 1 unknown load factor, and analysis will be completed. And you remember I mentioned there is limitation in the Lego fit force. We could not consider the creep and shrinkage, but in case of the unknown load factor, we can consider both creep and shrinkage effect and also large deformation effect. So all these effects can be considered with the unknown load factor. Actually, in the previous version, we could not consider the large deformation effect with the unknown load factor, but the latest released version, I mean the version that you are currently using, we can now consider the large deformation effect and the creep and shrinkage unknown load factor at the same time. So how we can consider it? There are 2 ways of the modeling method. So first method is creating the stage in which the only cable are activated, and the stage duration we should set as 0, and then specify the stage as unknown, just like checking on this. That is one way, or the other way is make the additional step, save the results of the additional step and the stage results, and then activate that cable in the first step of the stage, and then specify that first step in the unknown. Let me show you with the model how we can define that. So this is the modeling method 2. So firstly, we should save each of the construction stage with the additional step and the stage. So for each of the steps, we have checked all these options, and then in the unknown load factor, so select the first step. So cable will be activated in the first step, and also select the first step in this unknown. So program will try to find the unknown load factor for these stages. So with the limited value, and then program will give you the unknown load factor. So that is the new method with the latest version that we made the update. So that was the method how MIDAS considers in the how MIDAS calculates the cable force using the Lego fit force and the unknown load factor. So there was limitation in the Lego fit force that we could not consider the clip and shrinkage effect. But with the unknown load factor, so we were able to consider both large deformation effect and the clip and shrinkage effect. Now I want to move to the Camber issue. Camber is important issue for the cable state bridge as well, not only the segmental bridge but also cable state bridge. So how we can calculate the camber in MIDAS? Camber refers to the pre-fabricated or pre-designed shape which enable the member maintain the stress-free state in order for the member to reach to the targeted shape at the specified time. So camber value can be predicted using the deformation at the final construction stage. There are two different types of the camber. As you know, one is manufactured camber and the other is construction camber, and both can be obtained in MIDAS. In manufactured camber, important thing is the tangential displacement should be considered. But in the construction camber, tangential displacement can be adjusted with the leveling of the formwork. So only the net deformation is important. So deformation will be differently calculated in case of the manufactured camber and the construction camber. How we can calculate the manufactured camber including the tangential displacement? If you go to the construction stage analysis control dialog box, you remember this option which was right above the Lego fit force, initial tangent displacement for erected structure. Once we check on this option and perform analysis, this field will be activated, which means the program will give you the summation of the net displacement and the tangential displacement. So by checking on this option, we can get the manufactured camber result. In case of the construction camber, just without checking on this option, we can simply check the deformation in certain stage. That is the construction camber. Let me show you with the program better. So in this model, in the final construction stage, dz, which is the deformation in this gravity direction, I could get the deformation like this. In the node number starting from 5, you can see the deformation here. So this table, camber table, is provided by the program, and also this graph is also provided, and exactly same value can be also checked with the final construction stage as the deformation value. That is the construction camber. So for example, in this model again, you can specify the camber control here. I have defined two different structural group, camber 1 and 2. Camber 1 is this left part, camber 2 is right part up to the key segment. And then this left part construction order is like this minus dz dx order. Camber 2 construction order is in this direction, which is the positive dx direction. So specify the construction direction among these. After that, you can get the camber graph for the manufactured camber or the construction camber, and also the table value. Same for the manufactured and the construction. So this construction camber value is the value how much we should install above from the initial state. And this value can be actually checked in the model file. If we go to the final construction stage, and if we check the value of this nodes, they are the value that we just checked for the construction camber. And what about the manufactured camber? Manufactured camber, as mentioned, this value should include the tangential displacement. So tangential displacement can be checked with this function. In the construction stage analysis control, firstly we checked on this option, and the deformation in the final stage, we could check the stage step real displacement, and these values are the one we could check with the manufactured camber value. So including the tangential displacement, this manufactured camber can be obtained. And after engineers obtain the camber, then what will be the next step for them? They may want to verify if my camber value is correct or not. I mean, if my final construction deformation becomes 0 if I apply this camber value. So for that, MIDAS Civil has added new function, camber for construction stage. So using this, if we select this deformation camber option, Let me show you for that. There is the new function here, the Camber for construction. So if I select this deformation camber, it means the program will automatically update the camber value to the model file. So if I apply it, then the calculated camber value can be updated here. So after the analysis, for this part, so we have the deformation previously, and if I include the camber displacement, as you can see, so we can finally get the zero deformation in my girder. So after updating the camber, how the deformation is being changed, we can check from here. For that also, we need to check on this option, apply camber displacements to CS. By checking on this option, this field will be activated and we can get the results, including the camber. So if engineers want to update the camber value into the model, then we can recommend them to use this camber function. So first one, the deformation camber was the one the program can automatically calculate the camber value, the D's value, and update it in the model. But if the engineer, they have their own camber value calculated from some other program or Excel file, and if they want to update that camber value into the civil, we can use other two options. So one option is specifying the start and end nodes and the maximum camber value. So using that, based on the polynomial function, the program will try to find the camber value. The parabolic curve equation using the two curve and the two nodes and the maximum camber value. And the other one is we can just directly enter for each of the nodes what is the camber value one by one. So this manual input is also available. Then this value will be updated in the final deformation. So let me make the little summary about the status and the limitation of MIDAS civil for the construction stage analysis. So we have the three different type of the analysis methods to finding the jacking force in MIDAS civil. One is performing the backward analysis, but this could not consider the creep and shrinkage effect, also large displacement effect. Here, large displacements, I'm referring three different nonlinear effects. One is lateral stiffness, and the other is axial stiffness, which is also called the sag effect. And the third one is the changes of the geometry, the large displacement. So these three effects I'm referring the large displacement is considered. And in the backward analysis, both of them could not considered. But if we think about the Lego fit force, so Lego fit force could consider the large displacement, but not the clip and shrinkage effect. Unknown load factor could consider both of them in the latest version. And when the cable element is used in the construction stage, how the element will be considered, which type of element will be considered. In the linear analysis, if the cable element is used, equivalent truss element will be applied, which means the only sag effect will be considered. But if we perform the larger displacement analysis in the construction stage analysis, in that case, true cardinally cable elements will be applied. So if we simply perform the construction stage analysis without this option, in the case, equivalent truss will be applied for the cables. But if we check on this option, cardinally elements will be applied. It means the program can consider the large deformation, lateral stiffness, and the sag effect. And depending on the concrete and steel girder, so in MIDAS, clip and shrinkage effect can be considered for the concrete girder. Sometimes engineer will ask if nonlinear gradient can be considered. This is actually same as the other type of the bridge, so surely we can consider the temperature gradient, and we could check the camber control function, and temporary support or temporary cable can be considered because just the definition of the construction sequence is very flexible, as you know. And also we can consider the cable tensioning in multiple steps. How to do that? Just applying the cable pre-tension load in the separate construction stage. Depending on the construction field condition, sometimes engineers may want to apply the multiple cable pre-tension in one cable. So that is surely available in MIDAS. Now I want to move to the post-construction stage. So we have discussed about the construction stage with the cable stayed bridge. After that, if we need to perform the moving load analysis or eigenvalue analysis or additional loads, linear stating loads, which is not applied in the construction sequence. In that case, we need to consider the additional loads in the post-CS after the construction is completed. But we want to consider the cable stiffness which has been found from the construction stage analysis. We do not want to start from the beginning in the post-CS, or we do not want to consider the totally different stiffness for the cables comparing to the construction stage and the post-construction stage. So how we can consider this identical stiffness obtained from the construction stage? Using this option, program can automatically enter the final stage member force into the initial force for the post-CS. So identical stiffness can be applied in the post-CS. So by simply checking on that option, which could find here. So by checking on this option, then program will provide this table which can be found in here. So if I define this option, okay, and then by performing analysis again, so values obtained from the final construction stage member force are entered here. And using this member force, the stiffness of the cable will be applied. But this is the cable element, and depending on the type of analysis, element is differently applied. I mean, in the post-CS, we have the cable element, and if I perform the nonlinear analysis, geometry nonlinear analysis, in that case, surely the elements can consider all these three effects: lateral stiffness, sag effect, and large displacement, which means element will act like the true cardinal element. But what about the linear static? In case of linear static, yeah, surely large displacement will not be considered, but since we considered the cable element, the program was able to consider the lateral stiffness and the sag effect. So that is good, and that it has no problem. But what about the eigenvalue or time history analysis? If we perform the analysis, the eigenvalue analysis, now we have some problem because program could not consider the sag effect. It was able to consider only the eigenvalue analysis for the vibration of the cable with certain mass. And moving load analysis could be the one of the typical type of analysis in the post-CS, but we could not consider the sag effect or lateral stiffness, which means that even though we model this cable element, when we perform the moving load analysis, element will be just like the truss element, not equivalent to truss, not the true cardinal. It's just like the truss. I mean the elements type as truss. So the problem is this type of element is different from the element type applied in the construction stage or the linear static load. So after performing moving load analysis, for designing, we need always the linear load combination. But since the element type is different, their stiffness are different, then we cannot apply the linear load combination. And also, for the eigenvalue analysis, the correct stiffness, considering the sag effect of the cable, could not be considered. So we had such problem in the previously. So in order to resolve this state, we have added one more function in the for cable state bridge, which is marked here, that you can find in the program here. Change cable element to equivalent truss element for post-CS. Looks a little similar, but it has better functionality as we can now consider the linear load combination. So if this option is checked on, program internally apply the geometric stiffness and the axial stiffness of the cable for post-CS. So, but the thing is, lateral stiffness and sag effect will be identically applied for the linear static, eigenvalue, or moving load settlement. They are all same, which means now we can consider the linear load combination for this type of the element. In order to do that linear load combination, we do not update the cable stiffness considering the additional load from this linear static load or the moving load, which means only the loads applied during the construction stage will be considered to calculate their stiffness. It's same for the sag effect. So for calculating the axial stiffness of the cable, so only the force applied in the construction sequence is considered. And this one stiffness is applied in the linear static analysis in post-CS or eigenvalue or moving load. So now we can consider the linear load combination for the static nodes and the moving nodes, since they are using the identical stiffness. So if any of the user asks how I can combine the results of the linear static and the moving load analysis, then you can recommend this option. If I make the summary for these two methods that I mentioned, one is using the initial element force table, and the other one is using this option. So when this option is checked on, so as mentioned, we consider the largest lateral stiffness and the sag effect for the linear static, eigenvalue, and moving load analysis. If this option is checked off, then that is the traditional way, and we may consider the initial element force table if we want to apply the cable stiffness obtained from the construction stage. In the case, in the linear static analysis, lateral stiffness and the sag effect is considered, but in the eigenvalue, no sag effect. In the moving load, they are considered as the truss. So all different elements will be applied by the analysis type. So we have checked how the MIDAS will consider the different type of the elements by different type of the analysis, and in which case we can consider the linear load combination. So we can now consider the eigenvalue analysis, and one is applying this option, the other is not applying it. Depending on this, different type of elements will be applied. And also we can consider the seismic analysis for this cable stayed bridge, and response spectrum or inelastic time history, boundary nonlinear, those dynamic analysis. So type of element is same here. So depending on the option here, different type of elements will be applied. For the pushover, which is the static analysis, and this element, just like this linear static, the element type will be applied. And in the structure with the multiple support, different time history function in terms of the ground acceleration can be applied to different supports. So in case of the long span bridge, when the distance between the pylon is large, arrival time of the seismic excitation varies. The effect can be considered using the multiple support excitation function in here. So we can specify the different function, or we can specify the different arrival time for each of the supports. But one limitation of this function is we cannot consider the nonlinear behavior of the member. So this will work with the linear time history analysis. And finally, the processing functions. So maximum value, or during the construction sequence, I think all of you are very familiar with these results, so I will not explain more details of that. And for the cable state bridge, so we provide the cable configuration. So we can easily check the total length, which is considering the cable elongation and unstrained length. So summation of these two will be provided. Also the amount of the sag and also the skewed angle can be obtained. Cable efficiency is also another useful function. So cable efficiency with the before of the initial cables and the after the cable is applied, pretension is applied. How the efficiency is calculated, we can check from this table, and you can see how this efficiency value is being calculated in the program, considering the value of the horizontal tension force and the length of the cords and the angle of the cable. Thank you.
Thank you.
Thank you.
Good night. Good night.
Thank you.
Good night.
Good night.